we're going to move right into our feature presentation, which is UHPC for bridge preservation. And for this, we have Jess Mendenhall and Samir Rabie from NJDOT Structural Value Solutions Unit, and they're going to be talking about ultra high performance concrete for bridge preservation. So with that, I'll turn it over to the presenters, and I know you're going to share your screen, so I'm going to stop sharing mine and turn it over to you.
Thanks for the introduction, Brandy.
You're welcome.
I guess you can hear me okay?
Yep.
Yeah, okay. All right. Good morning, everyone. We're going to present on NJDOT's ultra high performance concrete overlay research project. We've done this presentation a few times before, not for the stick or EDC, but for this version, we're going to emphasize UHPC overlays for bridge preservation and rehabilitation. So we're going to be discussing the project development, design, construction, some lessons learned, and also the post-installed evaluation program of the UHPC overlays. Next slide. Okay, so UHPC has become commonly used in many states throughout the U.S. for joint fill applications or the connections between prefabricated structural components. NJDOT has had a lot of experience with the use of the UHPC in these joint or connection applications for about the past 10 years. And we've had a lot of success with the material, and given its superior properties, we have been investigating the use of UHPC for other applications. So UHPC overlay application was considered after federal highway reporting on successful use at another state agency, and also there's quite an extensive use of UHPC overlays throughout several countries in Europe. UHPC overlays in the U.S., however, are considered an emerging application. So the focus of this project, again, was the use of UHPC overlay for preservation of existing bridge decks. And a brief project overview. We had 4 bridges in the project, about 48,000 square feet of deck area, and we had 2 separate construction contracts, a region north and a region south. And we had a separate contractor on each project. And I'll get into more details of the bridges, the specific details on the following slide. Okay, so many of you are probably already familiar with UHPC, but if you're not, I'm going to quickly go over some of the material details. So UHPC is a cementitious composite material. It's typically composed of Portland cement, supplementary cementitious materials, fine aggregates, water, high-strength steel fibers, and a series of chemical admixtures, and a common one is a superplasticizer. And unlike conventional concrete, there's no coarse aggregate, and you can see the image in the upper right that shows kind of the mass or the weight distribution of the typical components comparing conventional concrete and ultra high performance. There's an optimized dry material size gradation, and this allows for particle packing, and this gives it a lot of the superior durability properties. And UHPC has mechanical and durability properties that greatly exceed that of conventional concrete. Some of these properties are the compressive strength. There's an increased tensile strength, and there's also a behavior that you don't see in conventional concrete is a post-cracking tensile strength, and that's from the steel fibers that are distributed in the mix. Again, the durability properties are superior to that of conventional concrete, such as reduced permeability. UHPC for closure pores is formulated to be flowable and self-consolidating, and this can be poured into the joints with little or no vibration. UHPC formulations for overlays, however, are much stiffer, and they're considered a thixotropic material, and they can hold their shape given the grade and the cross slopes on the bridge deck. And you can see the photo in the bottom of the slide, showing the self-consolidating mixture on the left and the overlay mixture on the right. And essentially the overlay mixture under static conditions behaves like a solid, but when you agitate the overlay mixture or induce vibration, it flows and behaves more like a liquid. So there's definitely some differences in the workability of the mix. So some of the program background. So traditionally, NJDOT has performed reconstruction of primary bridge components after they become structurally deficient. So that being a deck replacement project or a superstructure replacement or a total replacement project. So if we look at bridge preservation, this will allow us to preserve existing bridge components that are in fair or good condition and extend their service life with a more minimal investment. When it comes to deck slab preservation, we have used various traditional or conventional overlays throughout the years, and we've had some mixed results with this with regard to the construction quality and also the long-term durability. So we've used asphalt overlays with waterproofing, bridge deck waterproof surface course, and also some conventional concrete overlay materials. The photo on the right is a conventional concrete overlay that's been installed on one of our bridge decks. It has nearly 40 years in service, which is impressive for an overlay. But you'll notice in the photo the overlay is spalling down to the underlying deck, and there's also a deck patch. So this particular bridge deck has been patched extensively over its service life. And considering traffic control and having a contractor come out to do this type of work, there's been an extensive long-term maintenance cost. And with the UHPC overlay, this is hopefully something that could be avoided. We can reduce the long-term maintenance costs. We have over 2,000 state-owned bridges in New Jersey, and as many of these bridges are aging and becoming structurally deficient, the department can really become inundated with costly reconstruction projects. So we do think it's important to put a focus on bridge preservation and try to take bridges that are still in decent shape and preserve, the primary components to avoid, being inundated with reconstruction. Some of the advantages of UHPC overlay, as we discussed, it has superior mechanical and durability properties, which a lot of these properties are ideal for a bridge deck, which has really severe exposure conditions of all the bridge components. Also, the service life, we anticipate a high service life of the UHPC overlay. And looking at the initial construction costs are higher, but we anticipate there may be a life cycle cost benefit, and we'll discuss that on a following slide. Some of the disadvantages, the cost of the overlay is high compared to conventional overlays. So for this project, we had an average cost of the overlay material itself of about $30 to $45 per square foot. And if we look at the total project costs, including traffic control and the roadway work and some of the additional bridge work, we had a cost of about $90 to $120 per square foot, which this cost is still less than the typical deck replacement project, but still much higher than conventional overlays. Also, there's a consideration of the contractor experience. So our prime contractors don't have experience with UHPC in the overlay application. They do have experience using UHPC enclosure pours. However, there are specialty UHPC subcontractors that will have this experience. Also, workability of the mix. It's not necessarily a disadvantage, but it is something that needs to be considered. The overlay mixture may require specialty equipment and has slower finishing rates than other overlays. Okay, so now we want to talk a little bit about comparing deck preservation using a UHPC overlay versus, deck reconstruction or a deck replacement. So some things you want to consider, one is the existing conditions and the remaining service life of the structural components. that being the deck slab and the superstructure and the substructure. So if you're using a UHPC overlay, you anticipate a long service life, and you want to ensure that these other components will be able to be maintained for the life of the overlay. Otherwise, you're not using the investment into the UHPC overlay optimally. You also want to do a remaining service life determination of the structural components, considering their age, doing hands-on inspections, potentially non-destructive testing or evaluation. And also you can do concrete core testing of concrete components and get an estimate of the remaining service life from lab testing. You want to consider the initial cost and the life cycle costs and compare different alternatives, including preservation, rehabilitation, and also reconstruction alternatives. And looking at the typical decision process, so you would look to rehabilitate or preserve a deck that is generally in fair or better condition. And you would look to replace a deck that is considered to be in poor condition, and it may be extensively contaminated or deteriorated throughout the depth of the deck. So I get a target bridge would be a remaining service life. If you're gonna rehabilitate the deck slab for a UHPC overlay, we would anticipate approximately 40-year service life, and you want to make sure that the superstructure and the substructure remaining service life with or without rehabilitation will be comparable. Okay, so an example of a life cycle cost analysis, a general example. So if we look at a bridge that was constructed in 1990, approximately 8,000 square feet of deck area, and kind of a typical highway bridge, single span multi-girder bridge, some of the assumptions that we could look at is, okay, overall, all the structural components are in fair condition. We're going to assume that we're going to do repairs to the superstructure and the substructure for either alternative to increase the remaining service life. Assume a 40-year service life of the UHPC overlay, and then only for this cost comparison, we're going to look at structural costs only and consider that we're going to do routine maintenance on the bridge. So the first alternative would be to do a UHPC overlay now. The bridge is in fair condition, so we can consider a UHPC overlay and rehab the other components. And the second alternative would be to do nothing now and replace the deck in, say 10 years, when we'll assume that the bridge will drop into a poor condition. So the alternative two is kind of our typical thought process that we use. We move in to do a reconstruction when the bridge becomes structurally deficient. So those are the two alternatives that we're going to consider. So we did a cost analysis and a life cycle cost analysis for this example bridge. So looking at the initial construction cost, the UHPC overlay for doing the deck work only is approximately $480,000 to $500,000. If we were to do a deck replacement based on cost of other comparable projects, we would be looking at, for this bridge, approximately $1.1 million. For this is for the initial construction cost. Now, over the life cycle cost over a 100-year analysis period, for the UHPC overlay alternative, we have a 100-year life cycle cost of $7.2 million. And for the deck replacement alternative, a life cycle cost of $7.7 million. So initial construction costs, it's relatively significant cost difference favoring the UHPC overlay. The 100-year life cycle cost, clearly the UHPC overlay has a lower life cycle cost, and we use some conservative assumptions. So, with a life cycle cost, it's heavily based on the assumptions that you make. So potentially this could be an increased savings or a decreased savings depending on those assumptions. So I don't want to focus too much on the exact numbers on this slide, but I guess we're just trying to emphasize to, do an analysis of the initial construction costs and also look at a life cycle cost analysis to compare preservation versus reconstruction projects. Okay, so back to some of the details of our research project. I'm going to talk a little bit about the bridge selection process that we used during the project development. And these are 4 photos of the bridges that were ultimately included in the project. So during the project development, we screened dozens of bridges. Eight structures were shortlisted and they were fully evaluated and tested. And I'll talk a little bit more about that evaluation on a following slide. 4 structures were advanced into the design and construction. So some of the considerations for the candidate bridges, looking at the condition ratings of the primary structural components, we were looking for bridges that were in fair or good condition ratings. And, kind of repeating some of what I mentioned before, we wanted to ensure there was adequate remaining service life of the structure. We were looking for decks that didn't have signs of extensive deterioration, no underdeck spalling or chloride contamination. And for this research project, we wanted to keep the scope of the work to the overlay and avoid having to do extensive repairs to the other components. The focus of the project was on the UHPC overlay. So all bridges that were ultimately selected had an existing asphalt overlay, and we wanted to avoid decks that had an extensive depth of this overlay. Another consideration, given the high anticipated service life of UHPC, we want to ensure that the bridge will be functionally adequate for the long term. So looking at things such as load ratings, the power pits and the safety features, and the roadway widths and clearances, you're going to want to make sure that those are going to be acceptable in the long term, and you're not going to have to come back in after installing a UHPC overlay and do a widening or reconstruction and get the most for the investment. Some reasons bridges were eliminated. After doing evaluation, we determined there was extensive deck chloride content. And also the traffic impacts. This was a staged construction job, so if taking a long-term lane closure was something that was deemed to be, unacceptable or we wanted to avoid for the research project, that was another reason some bridges were eliminated. Okay, so this is a table of the 4 bridges that were included in the contract. Some things to note, we had 2 bridges with decks that were relatively new, approximately 10 years in age, and we also had 2 bridges with deck slabs that were approximately 30 to 40 years in age and towards the end of anticipated service life. We had a range in the deck slab areas. Again, all bridges had existing asphalt overlay, and the condition ratings of all of the primary components were good or better. So to talk a little bit about the evaluation that we did on the 8 candidate bridges, we took concrete cores on the bridge decks. We did 3 cores on each bridge deck, and this was to get an accurate estimate of the existing overlay thickness and also take chloride profiles at various levels through the deck, and this was done with chloride lab testing. We also used GPR, ground penetrating radar, to ascertain the overall condition of the deck and get an idea of if there's any variations in the overlay thicknesses, and also to get an estimate after doing the hydrodemolition if there's going to be any areas that may require full depth spall repairs. So I'm going to go over some of the key aspects of the design. For this project, we had some environmental constraints. It was a limited scope project, and one of our constraints was to match the existing and proposed elevations. So, as I mentioned before, all of these bridges were asphalt overlaid, so we had to consider options to maintain the final top of deck grade, but also avoid excessive thicknesses of the UHPC overlay. So for this project, we used a thin bonded UHPC overlay. Based on FHWA research, the UHPC overlays can be a minimum of 1 inch, but for this project, we use an average of about 1.5 inches to account for construction tolerances. The structures that had an existing asphalt overlay that was greater than 3 inches were designed with a 1.5 inch UHPC overlay with an asphalt topping, again, to minimize the UHPC quantities while maintaining the grades. One of the bridges, the NJ159 bridge, was designed with a 2.5 inch UHPC overlay with no asphalt topping. Asphalt topping on top of UHPC overlays is common practice in Europe. And another key aspect of this project, we did not rely on the strength provided by UHPC. It was solely for durability properties, but that's something that we are going to consider for future projects. Okay, so after the existing overlays were removed on the bridges, we specified a hydrodemolition to remove the upper half inch of the existing deck surface. Based on FHWA research and reporting, hydrodemolition is the preferred choice for surface preparation for the bridge deck to bond with the UHPC overlay. It creates an ideal bonding surface that's very rough and limited microfractures that can really affect the bond performance. Now, looking at other technologies such as diamond grinding or milling, they can be used, but they do induce microfractures, and that can affect the long-term performance and bond of the overlay. So for this project and for future projects, we're going to specify hydrodemolition. And you can see the photo here of a typical concrete surface after hydrodemolition. It's a very rough surface. You have exposed aggregates, and it also removes deteriorated areas of the deck slab. So as I mentioned before, this overlay was installed in 2 stages for all bridges. So a stage line construction joint was used to combine the stage 1 and stage 2 overlay. The joint detail that you see on the screen was used in our project and was developed from a European standard and provides detailing to prevent water intrusion and also provides structural continuity in the deck slab. An exposed fiber finish was specified between stage 1 and stage 2 overlay to promote bonding. And previous research has shown that a poor bond between the hardened UHPC in stage 1 and the fresh UHPC in the stage 2, you get a poor bond unless you provide an exposed aggregate finish. So on a following slide, Samer will be showing you a photo of this construction section. So for the deck joints, some of the deck joints on the project, so essentially the end of the deck slab and the abutment header, were removed full depth and reconstructed the full depth with UHPC. From our past experience, this location of the bridge is particularly susceptible to deterioration and spalling, so we wanted to reinforce the area with UHPC. And Samer will discuss some of the lessons learned on this particular detail later in the presentation. So that's it for my part of the presentation. Now I'm going to pass it off to Samer, and he's going to finish the presentation. Thank you.
All right, thank you, Jess. I'm Samer Rabie. Good morning again, everyone. And for the remainder of the slides, we'll cover the special provisions, the construction, the lessons learned, and the evaluation program. Starting with the material testing, the UHPC mixes consisted of a partial premix made by the supplier, including sand, water, liquid admixtures, and steel fibers at 3.25% of the total dry volume. The results of the acceptance test shown on the slide were provided in a submittal package. Due to the global pandemic at the time of testing and verification, there were no feasible labs for this project at the time of construction to provide some of the certified tests from FHWA publications. Meeting the acceptance criteria while having this challenge led to the acceptance of alternative test methods pursued by the supplier, including the bond strength by pull-off and direct tension tests. To ensure the consistency of each batch, a procedure of flow testing in accordance to ASTM C1437 was followed. For fresh properties, the dynamic flow test is measured by dropping the flow table 20 times continuously over a period of 10 seconds, and the average is recorded. With 3.25% steel fibers, the values of the static and dynamic flows were 4 to 6 inches and 6 to 8 inches, respectively. Overlay material is often challenging to control for contractors, regardless of what the material is used. Per the contract document, contractors were required to successfully place a 4-foot by 12-foot by 3-inch deep rectangular test slab of UHPC with a grade of 8% in the longitudinal direction. While this may not be appropriate or necessary for all sites, it should be considered to account for specific project needs, such as the profile grade, cross slopes, and complex geometric conditions related to large skew angles. In the images here, supplier X on the left failed to pass the mock-up test. Subsequently, the contractor invited supplier Y. The actual placement of the UHPC overlay does not require high level of skill, and the placement and finishing skills should be confirmed, attained, or fine-tuned during the mock-up test. Hydromilling was used to remove 1/2 inch of the top of the existing concrete decks, as well as the full depth removal of the existing headers. This provides a rough profile for the UHPC to bond to, removes surfaces exposed to the vehicles and asphalt oils, and also protects reinforcement in the deck in the event it is encountered shallower than anticipated. Hydrodemolition spoils and water are required to be hauled off-site to a treatment facility unless permits are obtained for a project for alternative disposal methods. Disposal to public sewage or drainage facilities is strictly forbidden. Specifications should clarify that the cost for any disposal of demolition material must be included in the bid price of the demolition pay item. A specialized contractor brings in prior experience placing UHPC, has established relationships with the UHPC suppliers, and has specialized equipment. A specialized UHPC placement contractor was used as a subcontractor to the general contractor, part of Contract A in Region North, but not for Contract B in Region South. More contractors are expected to join this industry, allowing more competition and competitive bid pricing. To the extent that a specialized UHPC paver is desired or needed, the specialized UHPC pavers are available for purchase by any contractor. This may be the case for overlay thicknesses greater than 2 inches. As long as the documents require the appropriate measures be taken by the contractor, along with the quality control requirements, the desired end product should be attainable by a general contractor or a specialized subcontractor. One thing we'd like to point out about this video is how the operation is maintained and it's continuing while there's traffic on the adjacent lanes, and how it helps with the staging without major impact to the flow. This is the 295 bridge. The contractor should provide how the screed will be set up, and achieve the required UHPC thicknesses to avoid potential thicker areas. While the designer shouldn't dictate the means and methods, it may be prudent to include an advisory note that high shear capacity mixers may be needed and should be considered while developing installation procedures. However, it is ultimately the contractor's means and methods to achieve the desired final results. The most crucial element is the mixing and establishing the correct amount of UHPC fluidity to ensure the UHPC holds the grade of the deck. This, however, will always be under the control of the UHPC supplier's experienced technicians, regardless of the presence of a specialty contractor. Exposed fiber finish at the construction joints should be emphasized in the contract drawings by requiring the exposed fiber finish work procedures be included in the work plan and must be submitted before the UHPC work starts. This includes the time for any fiber exposure work to be performed, since in one instance, this activity was delayed too long and the UHPC had gained most of its strength. An image of the desired surface should be included in the special provisions or the plans to help reduce any confusion. The contractor's work plan should also include procedure for installing key joint formwork early in the preparation of the construction joints and the stage line construction. Special provisions also require that all formwork in the UHPC must be non-absorbent, which can be achieved by using resin-coated products or wrapping formwork in plastic sheeting. With the mock-up tests and the shop drawings, the contractor should be required to identify the system and demonstrate how the sheeting will be secured if required. The consequences of an insecure system will not only compromise the final product, but could also result in safety concerns to the traffic on the adjacent lane. It is crucial to ensure proper curing in accordance with the specs and approved working drawing procedures to prevent dehydration cracks. Moving on to some of the lessons learned, starting with the scoping and concept development for future projects, we will identify locations that UHPC will serve as the final riding surface. This will allow for evaluation, inspection, and assigning more representative condition ratings in the future. If, however, an overlay on top of the UHPC must be provided for any reason, such as geometry or profile, we will consider the bridge deck waterproofing surface course, which is a performance spec, it's non-proprietary, and it does not require a waterproofing membrane. Another alternative could be the high-performance thin overlay materials. For the existing conditions, GPR can help determine concrete cover, overlay thicknesses, and reinforcement locations, as well as locate emerging spalls or delamination. This will help attain more accurate bids based on the deck repair limits. Two other items we are improving in our special provisions are additional language that during construction there should be emphasis on surveys for each interim stage to determine the actual depths of the hydrodemolition and the material quantities required for placement to ensure a continuous operation. The other item would be emphasis on specifying watertight forms, top forms, and the minimum of 1/4 to 1/2 inch overfill to help reduce the amount of surface deficiencies. The contractor is responsible for determining the appropriate overpool thickness. This could result in higher bids, but additional material quantities are not expected to result in substantial cost impacts. After observing the difficulties of the header demolition and construction, we have two alternatives moving forward. Using the flowable self-leveling UHPC for the full depth of the header placement to ensure proper consolidation around tight corners and reinforcement. The other alternative is a hybrid system of partial depth, high-performance concrete headers with UHPC over the top surface to provide the same overlay thickness over the entire structure. This will help mitigate some constraints and staging and schedule allowance. Two of the 4 bridges in both contracts experienced air voids or dehydration cracks or shrinkage cracks, which we are collectively referring to as surface defects, as shown on the image on the right. The UHPC slurry with no fibers was placed in the identified air voids. Since the voids contained overlapping exposed fibers, it was considered to create adequate bonding with the UHPC slurry. All the surface defects were addressed before asphalt paving, except for one structure where the UHPC overlay serves as the final riding surface. Out of an abundance of caution, these locations were identified for future monitoring. Also, these cracks were not observed when the sheeting was properly installed and secured, as shown on the image in the sensor. So for the evaluation program to assess the performance of the UHPC overlay, we put together a testing program to include non-destructive testing as well as physical sampling and lab testing. This objective will be accomplished by first establishing baseline conditions through an initial survey, followed by periodic monitoring of the UHPC overlaid bridges over succeeding years. This will give us some understanding of the deterioration rates, which will be beneficial in determining the life cycle cost analysis, as just discussed, during decision-making and alternative selection. The 2 bridges that were selected was the 295 bridge with the asphalt overlay on top of the UHPC, and the 159 bridge westbound, which had the UHPC exposed surface. For the non-destructive testing, we first looked at GPR, which was used. However, the GPR signal was scattered significantly, and the 3D rendering was ineffective due to the presence of the steel fibers in a random configuration in the concrete. So we moved to the impact echo and ultrasonic shear wave tomography. For physical sampling, we used the pull-off strength to give us the pull-off testing to give us the bond strength, and more importantly, the failure modes. Also, we did the chloride content to understand the permeability. This is a sample plan sheet. Most of these locations were either identified during construction, or they are areas of interest to our unit, which are at the construction joint or the negative moment region in the case of this bridge. During an impact echo test, the surface of the concrete is impacted to generate stress waves. The response signals, when analyzed, include a range of frequencies corresponding to the element thicknesses, reinforcement, delamination, and geometric boundaries. The impact echo testing was applied on a point-wide basis over a 2-foot by 2-foot grid at various locations along the bridge. On the graph shown, the horizontal axis shows the distance from the beginning of the grid, increasing towards the east, and the vertical axis shows the dominant frequency in kilohertz. In most cases, the dominant frequency was approximately 6 kilohertz, with the exception of 2 lines. With this line being clear at this area at 6 kilohertz, this gives us an indication that the bond between the asphalt overlay and the UHPC is intact, as well as the bond between the UHPC overlay and the substrate or existing concrete. At 2 locations, we were not able to get that dominant frequency, giving us an indication that there might be delamination or debonding at these areas. These areas were identified and were included in the succeeding year testing program. Shear wave tomography involves the propagation of shear stress waves, or S waves, through the concrete, transmitted and received by an array of transducers. Analysis of the signal times and angles allows for the construction of a 3D representation of embedded features. The transducers are spring-loaded, allowing for the testing of uneven surfaces, unlike the impact echo. So for the 159 bridge with the exposed deck, we were not able to perform the impact echo test because the width of the grooves on the deck corresponded to the dimensions of the impactor. That's why we moved to the ultrasonic shear wave tomography. This data was collected on a grid as well at 6 inches by 4 inches to construct the 3D representation, and the test sections were used to complement the impact echo findings for the 295 bridge. The data is collected at a series of shots, step by step, on a grid. The asphalt concrete bond appears to be sound, therefore the reinforcing bars are clear, as we can see here. There were no further discontinuities observed below this depth, indicating an intact bond between the original concrete deck and the new UHPC overlay. The non-structural bond between the asphalt layer and the concrete was weak at a few locations, blocking the majority of the signals, as we can see over here, where this reinforcement is masked as compared to the one next to it. And these areas were also marked and identified for the succeeding program. The table on the left is showing the results from the pull-off testing. There are 4 modes of failure. Failure mode A, which is at the substrate. Failure mode B, which is at the concrete interface. Failure mode C, which is within the overlay. And failure mode D, which is at the epoxy interface. At the beginning, most of the failures were for failure mode D for us until we nailed down the epoxy that we need to use, as well as the curing times, after which we got the desired results of failure mode A, except for a few locations where we got failure mode C, and those areas were also identified. For the chloride contents, the segments were taken at 2 depths, at 1/2 inch, which is within the UHPC overlay, and 1 inch, which is below the UHPC overlay. Generally, the chloride contents were considerably lower than the 2 pounds per cubic yard threshold to initiate corrosion per our NJDOT bridge design manual, except for core C2. which had very high concentrations of chloride. Potential cause for C2's unexpected high chloride content may be due to the area from which it was extracted. Properties such as the location, geometry, condition, to name a few, may have led to the pooling of water or salt water within the area of core C2. Finally, to conclude, the ultrasonic shear wave thermography and impact echo testing indicated that the bond between the UHPC and the concrete substrate is in fact intact. Bond strength test data demonstrates that the desired bond was achieved between the UHPC and the substrate concrete. Chloride content, for the most part, were also within expectations. The baseline testing was successful with no significant defects encountered. For future monitoring at the same locations as well as other locations to maximize the testing area. And NJDOT is considering installing UHPC overlays on newly constructed decks, as well as decks with lower condition ratings for future projects. A deeper overlay with deeper existing deck removal will be regarded as a viable alternative for the structures that need major deck rehabilitation. Finally, we are incorporating UHPC for several applications in the new design manual, including preservation and repair. And through our Bridge Resource Program, we're also working with universities to produce non-proprietary, locally sourced UHPC to drive down the cost and increase the applications. Finally, we'd like to thank all the teams that helped materialize this project. Thank you for the STIC folks for inviting us to give this presentation. I will be happy to take any questions.
Thank you, Jess and Samer. If there's any questions, we'll just give a few seconds for people to ask. I think I saw a few things pop up in the chat, but I don't know if they were answered or not. So just take a look in there and see if there's anything. But otherwise, people can just go ahead and ask any questions of the presenters.
Okay, so one of the questions here from Ali, what is the approximate service life of the UHPC overlay? You know, we considered about a 40-year service life for the life cycle cost analysis. I think it's highly dependent on the looking at the, if you're using it for preservation, looking at the underlying deck and, you know, ensuring that you know, if you put the UHPC overlay and it should prevent further chloride ingress or moisture ingress. So even if you have already have chloride contamination or corrosion issues, those we anticipate that those would cease. But if you have a deck slab that doesn't have those issues, it's not extensively chloride contaminated, the overlay is going to really cut off those contaminants. So, you know, realistically, we think we could get more than 40 years out of it, but you know, other components of the bridge are going to deteriorate, and they're going to require replacement, or the bridge will be functionally obsolete. And we think that that's ultimately what's going to limit the service life. I mean, these materials and testing, they have some UHPC samples that FHWA has tested since the 90s and had them essentially ponded in chloride baths, and there's been no, you know, essentially no deterioration detected. I mean, it's really an impermeable material. But yeah, for our analysis, we considered about 40 years. And the second part of that question, what is the surface preparation? You know, I know we covered that. Hydrodemolition is what's recommended. It provides a, you know, superior bonding surface. And a big thing is when you're demoing a deck, it removes all unsound concrete. So, you know, you don't want any unsound concrete interfacing with the overlay material, and you want to have the adequate bond. So hydrodemolition is what we used, and that's what's recommended for future projects.
Okay, and any other questions for our presenters?
And then there's another question from Ali. Could you discuss the tension contribution of UHPC overlay to the deck in the negative moment region? So UHPC, it has has a much larger tensile resistance than standard concrete. So standard concrete for design, it's normally the tensile resistance is normally disregarded. UHPC, I think you can get up to maybe 700 psi before it starts cracking. And then when it begins to crack, the steel fibers take over, and then there's even an increase in the tensile resistance after post cracking. And that's not something we considered for this project. There are draft design guidance that AASHTO and FHWA are working on. They're not published yet, but you can, if you have the adequate interface bond, you could rely on UHPC for tensile capacity, and that's something that we could probably do in a future project if we wanted to strengthen the deck, or if we put the overlay in on a new deck slab and wanted to rely on that for the deck capacity. So there are draft design procedures for that. And I guess in short, conventional concrete, you would ignore any tensile resistance, but UHPC, that could be relied on in the design.
And I can add to that this is also one of the objectives of the evaluation program, is to understand the deterioration rates. We haven't, there isn't a publication, for example, of this in an existing condition, in a site condition outside of a controlled lab environment. So this is also one of the drivers for the evaluation program that we're also seeking funding to maintain throughout 2026.
Okay, thank you both so much. I'm sure if there's any other questions that come to mind, you could pop them in the chat, or we can provide some contact information for Jess and Samir, and we can pass that on. So